Good evening, friends. Welcome to our evening lecture on numerical integration. I am sad to say that the TA strike continues, so during the duration, I will continue to do these lectures in the evenings typically. So check your email to see when and where I will be. But I hope you had a nice spring break, and I sincerely hope we get ourselves back to class right away. That would be very nice. And I appreciate the small number of you to be here live tonight. So if you have any questions or comments, please post them in the comment section, and I'll do my best to answer them. All right, let's get ourselves started. In our last lecture, we took a look at some Taylor series, Taylor and Maclaurin series. And I want to remind us of what some of those were. And then we'll actually do an approximate integral on one of them. So our favorite is e to the x, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, x to the 4 over 4 factorial, x to the 5th over 5 factorial, etc. That's kind of our basic one. And then we have cosine x, which is the even powers alternating. So starting with 1, skipping the first order, minus x squared over 2 factorial, skipping the third one, plus x to the 4th over 4 factorial, skipping the 5th one, minus x to the 6th over 6 factorial, etc. And sine x gives us the odd value. So starting with x, skipping the second, minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial, plus dot, dot, dot. In all cases, in all of 3 of these cases, the interval of convergence is all real numbers. So that's kind of nice. It extends well. So minus infinity to plus infinity are all real numbers. So these are our favorite Taylor series, centered at 0, also known as Maclaurin series. But we can look at natural log of x centered at 1. We can look at inverse tangent of x. We can look at 1 over 1 minus x. Maybe that's a good one to look at. 1 over 1 minus x. First term is 1. Common ratio is x. Is 1 plus x squared plus x cubed plus dot, dot, dot. Notice your common ratio is x. So my interval of convergence here is what? From minus 1 to 1. So that's not quite as useful, but I want to take a look at the e to the x thing that we have. And here's going to be my goal. I want to integrate from 0 to 1 e to the negative x squared. So this is one of our favorite functions, and let's take a look at how we can do that. So goal, let's find the integral from 0 to 1 of e to the negative x squared dx. So to do that, I want to get an approximation for e to the negative x squared. I have e to the x here. So what will e to the negative x squared be? Replace all of your x's with negative x squared. So that's 1 plus negative x squared plus negative x squared over 2 factorial plus negative x squared to the 3rd over 3 factorial plus negative x squared to the 4th over 4 factorial plus negative x squared to the 5th over 5 factorial plus dot, dot, dot. So if I'm just going to use the first few terms, then I can say that e to the negative x squared is approximately, in a sense, 1 minus x squared. A negative squared becomes positive plus x to the 4th over 2 factorial. X squared is x to the 6th minus is minus. X to the 6th over 3 factorial plus x to the 8th over 4 factorial minus x to the 10th over 5 factorial. So that's an approximation for e to the negative x squared. That is the 10th order Taylor polynomial for e to the negative x squared. So if I want to take the integral from 0 to 1, remember that's our goal. I would integrate this from 0 to 1 and see how close I'm going to get. So using a numerical approximation, in a sense, we're going to take the integral from 0 to 1 of e to the negative x squared dx. Should be approximately the integral from 0 to 1 of all that. 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial plus x to the 8th over 4 factorial minus x to the 10th over 5 factorial dx. So that should be our approximation for the integral. Now, there is no closed form antiderivative. If I try to take the integral of e to the negative x squared, I am not going to be successful. There is no antiderivative I can use. But this should give us a pretty good approximation. So let's see how this is going to work. So what does that in turn equal? That in turn equals x minus x cubed over 3 plus x to the 5th over 5 times 2 factorial minus x to the 7th over 7 times 3 factorial plus x to the 9th over 9 times 4 factorial minus x to the 10th over 10 times 5 factorial, evaluated as x goes from 0 to 1. So this should be our approximation for e to the negative x squared. And let's see how close we are to a correct answer. So if I plug in 1, I get 1 minus a third minus 1 over 5 times 2 factorial minus 1 over 7 times 3 factorial minus 1 over 9 times 4 factorial minus 1 over 10 times 5 factorial. If I plug in 0, 0, 0, 0, 0, 0, 0. It's just minus 0. So to do this, all I've got to do is go ahead and do all that stuff. So let's see if I can get there. So can you see this? I'm not sure you can, but we'll give it a try. So I have 1 minus 1 over 3 minus 1 over 5 times 2 factorial, which is just 2, minus 1 over 7 times 3 factorial. 3 times 2 times 1 is 6. Got a sign issue here somewhere. This should be minus. That, of course, is plus. That's minus. That's plus. That's minus. So let me fix that. 1 minus a third plus 1 over 5 times 2 factorial minus 1 over 7 times 3 factorial plus 1 over 9 times 4 factorial. 4 times 3 is 12. 2 is 24. Minus 1 over 10 times 5 factorial. And what do I get? 0.74665 approximately. I don't know if that's close to the right answer. We'll take a look. So based on that approximation, I'm that this is in the neighborhood of 0.747 when I rounded to 3 decimal places. But remember, the question was the integral from 0 to 1 of e to the negative x squared. So let me go ahead and ask the calculator to do that. Integral from 0 to 1 of e to the negative x squared, e to the negative x squared, with respect to x. Are we in the same ballpark? 7468, 7466, I'd say that's pretty good. So we have a decent numerical approximation for that integral by using the Taylor series that we developed in our last lesson. But today's lesson is going to be on 2 other techniques that we're going to use to find approximate integrals, namely the trapezoidal rule and Simpson's rule. 2 other strategies we will use to find approximate values for integrals, because many, many times there's no way for us to find the exact value. So here is what we're going to take a look at first. We got to remind you of some basics from geometry. We're going to say use the trapezoidal rule. And you can't quite see that, and we'll move it in. Use the trapezoidal rule. I made a mistake, x to the 11th over, I sure did make a mistake. Thank you. Should have been x to the 11th over 11. So let's see if I can fix that on my last problem. Appreciate the connection. So that should be minus 1 over 11 times 5 factorial. And I get 7467 instead, which again is very close to my answer of 7468. It's even a better answer. So I appreciate the correction on the error on the last example. All right, let's go ahead and go back to our problem on using the trapezoidal rule. So use the trapezoidal rule with n equals 4 to approximate the following. To approximate the integral from 0 to 2 of x squared plus 1 dx. Now, here's the thing. We could do this precisely. Using the fundamental theorem of calculus, we can find an exact answer. So this will give us a way for us to see just how good our approximation is. We want to make sure that we're connecting this to the geometry. So what does this look like? Area under the curve. X squared plus 1 is a parabola. So it's starting at 1, and it's going up to 5. So I've got 0, and I've got 2. And I'm interested in the area under that curve. But you'll notice I said n equals 4. That means I'm going to use 4 trapezoids. So putting those in, trapezoid 1 will be defined here. Trapezoid 2 will be defined here. Trapezoid 3 will be defined here. And trapezoid 4 will be defined there. Now, we've got to remember what a trapezoid is and how we find the area of a trapezoid. So let me just give you a quick reminder. This is what we usually remember. This is base 1. This is base 2. And this is the height. So I have a trapezoid like this, and I have a trapezoid like that, or excuse me, sides of the trapezoid. So the area of that trapezoid is the average of the bases, 1/2 base 1 plus base 2 times the height. So the average of the bases times the height is our formula for a trapezoid, except here our trapezoids look like this. So if that's the case, this corresponds to the first base, this corresponds to the second base, and this corresponds to the height. And the area is still 1/2 base 1 plus base 2 times the height. Now, these things are not trapezoids as they're drawn now, but I can make them trapezoids by drawing a straight line from point to point. Straight line, here to here, straight line, there to there, straight line, there to there, straight line, there to there. So, I mean, you can see it's a pretty good approximation. We're just assuming that this is linear. So if it's not growing too fast, that may be a decent approximation. Not perfect, but it may be a decent approximation for us. So we need to figure out what the areas of all 4 of these trapezoids are going to be. We're going from 0 to 2, so I'll need to get the points of interest. So this is 1, this is 1/2, and this is 1.5 or 3/2. So trapezoid 1, what are my 2 bases? So for trapezoid 1, base 1 is the value of the function at 0, but the function is x squared plus 1, so that's 0 squared plus 1, which of course is just 1. Base 2 is f of 1/2, which is 1/2 squared plus 1, 1/4 plus 1, 4 quarters and 1/4, 5 quarters. And the height is 1/2. So you get the idea. But rather than just doing the computation, let's see if we can figure out what the general form will be. So I've got the area of trapezoid 1 is 1/2. The first base is f of 0. The second base is f of 1/2 times the height, which is 1/2. The area of trapezoid 2, The first base is f of a half. The second base is f of 1 times a half. The area of trapezoid 3, the first base is f of 1. The second one is f of 3 halves. 1 half f of 1 times the height. And then the area of trapezoid 4, is what? Area of trapezoid 4 is 1 half f of 3 halves plus f of 2 times 1 half. So the total area requires us to add all these pieces up. And you'll notice that if we add all these pieces up, we're going to see a pattern emerge. The pattern that emerges is we have 1 half here, and then we have this thing, which is the height. So this is 1 half always, and this is the height, and then we have f of 0 plus f of a half plus f of a half plus f of 1 plus f of 1 plus f of 3 halves plus f of 3 halves plus f of 2. And that will help us generate a formula for this process. So what are we going to say? The total area is approximately what? Total area is 1 half here times 1 half there, then add all this stuff up. F of 0 is there once, plus f of a half is there twice, 2 times f of a half, plus f of 1 is there twice, 2 times f of 1, plus f of 3 halves is there twice, 2 times f of 3 halves, plus f of 2 is just there once. So we can go ahead and evaluate this. We can go ahead and find our answers to make sense of this and see what we get. But I want you to recognize this. Always a 1 half and then always the height. So this piece is always 1 half. This piece is always the height, which is actually the width of the interval. Notice in our picture up here, this is the width of our interval. So height, or if you like, width of the interval. But then we have f of 0 once, 2, 2, 2, and then we finish up with a 1 again at the end. That is going to be the process we're going to use to find the area using the trapezoidal rule. Okay? So I will allow myself to get some assistance with my calculator. The function that we're dealing with here is, of course, x squared plus 1. Remember, our function f of x is x squared plus 1. That's what we're dealing with. So the numbers we're plugging in here are going to be x squared plus 1. But on an exam, you're not going to have access to a calculator, but we'll try to keep the computation reasonable, if at all possible. So total A, 1 half times 1 half. F of 0 is 1. 0 squared plus 1 is 1. F of a half, as we saw before, we said it was 5/4. 2 times 5/4. F of 1, 1 squared plus 1 is 2, plus 2 times 2. F of 3 halves, 3 halves squared is 9/4, plus 1 is 13/4. Plus f of 2, what is f of 2? 2 squared is 4, 4 plus 1 is 5. So we put all that together, what do we get? Trapezoidal rule look familiar? I hope so. 1, 2, 2, 2, 1. That's what we're dealing with the trapezoidal rule. So the total area is 1/4 times all of this, which I am getting 19 if I add all that stuff together. I'll let you check that. And I'm saying that that area is supposed to be 19/4. Now, I know that's not going to be right because we saw from our picture that this is an approximation. But we hope it's a reasonable approximation. So is 19/4 close to my answer? If we go back to the original question was the integral from 0 to 2 of x squared plus 1. So this is what we started with. Integral from 0 to 2 of x squared plus 1. So I can do that using the fundamental theorem of calculus. How close is that to 19/4? Integral from 0 to 2 of x squared plus 1. Antiderivative is x cubed over 3 plus x. Evaluated as I go from 0 to 2. 2 cubed over 3 plus 2. 8/3 plus 2, 6 and 8, 14/3. As a decimal, what is 14/3? 14/3 is 4.67 approximately. Whereas 19/4 is what? That was our approximation. 19/4 is 4.75. So my 4 trapezoids gave me an approximate answer of 4.75. My exact answer using the fundamental theorem of calculus was 4.67. If I wanted a better answer, I could have used more trapezoids. That's certainly one option. I used 4 trapezoids here to keep the computation reasonable, but I am certainly capable of finding more trapezoids if I am interested. All right, let's go ahead and do one more version of this trapezoidal rule here before we move on to our next rule, which will be Simpson's rule. So let me see what I have here in my notes. How about the integral from 0 to 2 of 3 to the x dx? So again, our goal is to use the trapezoidal rule. As I try to center my paper, that's pretty good. Use the trapezoidal rule. This time with n equals 6. To find the integral from 0 to 2 of 3 to the x dx. So let's go ahead and draw our picture. It's going to look similar to the one we just did, but this time we're breaking it up into 6 pieces, not just 4. 3 to the 0 is 1, and 3 to the 2 is 9, so clearly not drawn to scale. But we get the idea. We want to have 6 trapezoids this time. So here's 0, here's 2. We're going to split it in the middle here to get us to 1. Then I'm going to split it again, 1/3, 2/3. Here's 1/3, here's 2/3. I want you to recognize, similarly here, of course, 1 1/3, 4/3, 1 2/3, 5/3. So our width here is 1/3, but where does that come from? Our width is 1/3. The width that we need, the width of the trapezoid, which is actually the height in terms of our definition, is b minus a over n. Endpoint b, 2, minus starting point 0, 2 minus 0 over n, the number we're using, 6. So our width here is 1/3. Now remember how we did this. We have a base here. We have a base here. Here's our trapezoid. Here's our height, which is really the width. So this is base 1. This is base 2. So the area of the trapezoid is the average of the bases, 1/2 b1 plus b2 times the width, which is b minus a over n. So if I construct my 6 trapezoids, you'll notice the way this is bending, I will be too big again this time, just like I was in the last example. But I hope it's going to be pretty close. I hope it's going to be pretty close. So for trapezoid 1, my area of trapezoid 1 is 1/2. The first base, f of 0, f is 3 to the x. F of x is 3 to the x. 1/2 f of 0 plus f of 1/3. The average of the bases times the width. What's the width? The width is 1/3. The area of trapezoid 2 is going to be 1/2 f of 1/3 plus f of 2/3 times the width, which is 1/3. The area of trapezoid 3, trapezoid 1, trapezoid 2, trapezoid 3, trapezoid 4, trapezoid 5, trapezoid 6. Trapezoid 3, f of 2/3 plus f of 1 times the width, which is 1/3. Area of trapezoid 4, 1/2 f of 1 plus f of 4/3 times the width, which is 1/3. Area of trapezoid 5, 1/2 f of 4/3 plus f of 5/3 times 1/3, and area of trapezoid 6 is 1/2 f of 5/3 plus f of 2 times 1/3. I've got to add all of these up. Those all need to be added up to get my final answer. But you'll recognize there's a 1/2 times a 1/3 in all of them, so that the total area will be 1/2. We have f of 0 plus f of a third plus f of a third, 2 times f of a third. F of 2/3 is there twice. 2 times f of 2/3. F of 1 is there twice here and here. 2 times f of 1 plus 2 times f of 4/3 plus 2 times f of 5/3 plus 1 times f of 2, all multiplied by the width, which is 1/3. So by now, I hope you're seeing a pattern. 1, 2, 2, 2, 2, 2, 1. Those are our multipliers. 1/2 in the front, width on the back. So I should be able to get an approximation for this. I'm going to use my graphing calculator here. Again, my function f of x is 3 to the x. Note. F of x equals 3 to the x. So if I would write all this out, then I would say the total area based on 6 trapezoids is 1/2 3 to the 0 plus 2 times 3 to the 1/3 plus 2 times 3 to the 2/3 plus 2 times 3 to the first plus 2 times 3 to the 4/3 plus 2 times 3 to the 5/3 plus 1 times 3 to the second, all multiplied by 1/3. And let's see what that gives us. That should give us some kind of a number. So I'll quickly try that on my calculator and see what I get. So I have 1/2. Actually, make it 1/6 to make it a little bit easier. 3 to the 0 is 1, plus 2 times 3 to the 1/3, plus 2 times 3 to the 2/3, plus 2 times 3 to the first, plus 2 times 3 to the 4/3, plus 2 times 3 to the 5/3, plus 1 times 3 squared, and I'm getting an answer. I'm not really sure I believe. Let's take a quick look at it again. 3 to the second is 9. I'm getting about 7.36. We'll see if that's close. All right. Is there any compulsion to use trapezoidal rule with a particular question is what comes up on the comments. Well, you know, it's an approximation scheme. I did the approximate integral of e to the negative x squared. Many things cannot be integrated. In the real world, most functions cannot be integrated. So we need to use various numerical schemes. Is the trapezoidal rule a terribly good scheme? If that's what your question is, no, not really. It doesn't converge very quickly. Now, if I actually do the integral from 0 to 2 of 3 to the x on my calculator, 0 to 2 of 3 to the x dx. Is my 7.36 close, or did I make an error somewhere? I don't know if you can see any of that. Maybe you can see a little bit of that. Math, numerical integral from 0 to 2 of 3 to the x dx. And I get 7.28. Yeah, I feel pretty good about that then. So my scheme with 6 trapezoids gave me 7.36. The answer I get corrected 2 decimal places on the calculator is 7.28. So I feel pretty good. I feel pretty good about that. But trapezoidal rule is not necessarily our favorite rule. Let's try to clarify, though, what the trapezoidal rule is going to be. So let me give you a blue box, a rule you can use to sort of put all this together. But you've seen how we have a 1/2 here. You've seen how we have a width b minus a over n, and you see 1, 2, 2, 2, 2, 2, 1. So let's formalize the trapezoidal rule now that we've done it a few times to see how it is going to behave. So trapezoidal rule, what is it? Let's talk about it. Trapezoidal rule. Well, I mean, here's the deal. We're taking an integral from a to b of f of x dx. So if we start from a to b, here's a, here's b. We're going to divide it up into n pieces, okay? So we have n trapezoids. So you can see that the width, if we have n of them, the width is going to be minus a over n. Now, these values that we start with, we call a x sub 0, we call b x sub n, we call this guy x sub 1, we call this guy x sub 2, excuse me. And here's what our general form is going to be. The integral from a to b of f of x dx will be 1/2. That's our 1/2 average. B minus a over n, that's our width, times what? Times 1 times f of x naught, which is a, plus 2 times f of x1, plus 2 times f of x2, plus 2 times f of x3, plus dot, 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 plus 1 times f of xn. Make sure you can read that. That's a 1. That's f of xn, which of course is the same as b. I particularly don't really use this rule that way very much. I like to just go ahead and draw my trapezoids and get a feel for how they're behaving. To me, that is a better strategy for us to use. But there it is. There it is formally. 1/2 times b minus a over the n. Sometimes it's written this way. So one more time, integral from a to b of f of x dx is approximately equal to, by the trapezoidal rule, is approximately equal to b minus a over 2n. You can see why. B minus a over 2 is the width. B minus a over n is the width, 1/2 we need for our trapezoidal rule. And then we have f of x naught, which is f of a, plus 2 times f of x1, plus 2 times f of x2, plus dot, 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 plus f of b at the end. So 2's in the middle, f of a, f of b at the end of that discussion there. All right. Trapezoidal rule isn't bad, but we can do much better. We can do much better with something called Simpson's rule. So I want to go ahead and discuss that process. And we'll see how much better we get with Simpson's rule. So let us take a look at that process. I will tell you that the geometry that we use for Simpson's rule are parabolas, but I'm not going to develop that. That gets a little trickier. So let's use an example first to show Simpson's rule, then I'll develop the formal strategy. So here we go. Use Simpson's rule. To determine integral from 0 to 2 of x cubed dx. In my case here, I'm going to say n equals 4. Note, on Simpson's rule, n must be even. Four is certainly even, so that's a way for us to go. Now, let's draw ourselves a picture here. We are going from 0 to 2. At 0, we are starting at 0. At 2, 2 to the third is 8. So it's growing fairly quickly here, but I have n equals 4. So just like before, we had 4 trapezoids. These aren't really trapezoids we're using this time, but I wanted to find the various y values. I have 5 y values on this that I'm going to work off of. Right here, that's y sub 0. This guy is y sub 1. This guy is y sub 2. This guy is y sub 3. And this guy is y sub 4. Y sub 0, y sub 1, y sub 2, y sub 3, y sub 4. So that's the value of the function at the endpoints. But if we had trapezoids, the left and right side of the trapezoid, that would give us. So what is our formula? What are we going to take a look at? How are we going to make sense of this? Well, our integral from 0 to 2 of x cubed dx is going to be approximately the following. Change in x divided by 3, change in x is the width. So in this case, this is 0, this is 2, this is 1, this is 1/2, this is 3/2. In my example here, the change in x is 1/2. That's the width of the interval. And then remember how with trapezoid rule is 1, 2, 2, 2, 2, 2, 1. In Simpson's rule, it's 1, 4, 2, 4, 1. Or 1, 4, 2, 4, 2, 4, 2, 4, 1. Or 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. So 1 y sub 0, we have that, plus 4 y sub 1, plus 2 y sub 2, plus 4 y sub 3, plus 1 y sub 4. If we had gone out to n equals 6, just so I can make sure that you're seeing the pattern. If instead I had n equals 6, what would that be? That would be what? That would be change in x over 3, 1y0 plus 4y1 plus 2y2 plus 4y3 plus 2, 1, 4, 2, 4, 2, 4 plus 4y5 plus 1y6. So that's the process. 1, 4, 2, 4, 1, 1, 4, 2, 4, 2, 4, 1. That's what you've got to remember. So if I'm going to do this model for this problem, change in x, that's the width. Change in x is 1/2. So I'm not sure what's happening here. So I've got 1/2 divided by 3. 1 y sub 0. Well, remember, the function is x cubed, so 0 cubed, plus 4 times 1/2 cubed, plus 2 times 1 cubed, plus 4 times 3/2 cubed, plus 1 y4 is 2 cubed. So what do I have here? 1/2 divided by 3. 1/2 divided by 3 is 1/6. 0 plus 1/2 cubed is 1/8, so 4 times 1/8. 1 cubed is 1. 2 times 1 is 2. 3 cubed is what? 27/8. Plus 1 times 2 cubed is 8. What does that give me? 1/6 times 0 plus 4/8 is 1/2 plus 2. What is 4 times 27/8? 4 times 27/8 is 27/2. 8 and 2 is 10. 27/2 and 1/2 is 28 is 14. 10 and 14 is 24. Divided by 6. After all that, I am telling you that based on Simpson's rule, my answer is 4. The question is then, how good is that approximation? Is that close to my answer? Is that way off? You remember what we were asking for is the integral from 0 to 2 of x cubed dx. So let's do that to see how close that is to 4. Integral from 0 to 2 of x cubed dx. Integral from 0 to 2 of x cubed dx. Antiderivative is x to the 4th over 4. Evaluated as x goes from 0 to 2. 2 to the 4th over 4 minus 0. 16 over 4. Answer is 4. So in this case, it appears as if our answer is exactly right. So is that always the case? Most certainly not. That is not always the case, but it was in this circumstance. I think I have time to do one more Simpson's rule. So let's go back to the integral from 0 to 2 of 3 to the x dx. And this time let's use Simpson's rule with n equals 6. So here's what we're going to do in our waning minutes of our time this evening. So use Simpson's rule with n equals 6. How do you remember 1, 4, 2, 4, 1? Yeah, you know, you got to remember it. Just like in trapezoidal rule, 1, 2, 2, 2, 2, 2, 1. You're asking me what is delta x? In my computation, delta x is the width. It's b minus a over n. So I guess I could write that down for you. Use Simpson's rule with n equals 6 to approximate the integral from 0 to 2 of 3 to the x dx. So again, change in x in my problem is b minus a over n. In my example here, b is 2, a is 0, n is 6. So the change in x here is 1/3. I like to have a visual to see how this works. 3 to the 0 is 1, 3 to the 2 is 9. We want 6 of these. So that's what we have here. Here is 0, here is 2, here is 1, here's a third, there's 2/3, here's 4/3, here's 5/3. I need y sub 0. This is y sub 0. This is y sub 1. This is y sub 2. This is y sub 3. Y sub 4. Y sub 5. Y sub 6 is what we got here. What exactly is this? An approximation scheme. Oftentimes we cannot find integrals. We need a way to approximate them in the world of engineering, and numerical strategies are very useful for us in that world. Just so we're clear, y sub 0 is 3 to the 0. Y sub 1 is 3 to the 1/3. Y sub 2 is 3 to the 2/3. Y sub 3 is 3 to the 1. Y sub 4 is 3 to the 4/3. Y sub 5 is 3 to the 5/3. And y sub 6 is 3 to the 6/3, or 3 to the 2nd. So what is my strategy here? If we are using Simpson's rule to get this, what is my area going to be? Area is going to be change in x over 3. Remember, for trapezoidal rule, we had to multiply by 1/2. Here we're going to, multiply by 1/3. So our change in x is 1/3. Divided by 3 will give us a 9. Then I have y sub 0 plus 4 times y sub 1 plus 2 times y sub 2 plus 4 times y sub 3 plus 2 times y sub 4. 1, 4, 2, 4, 2 plus 4 times y sub 5 plus 1 times y sub 6. That's our strategy. So finishing this off, we are going to say that we get our area, change in x, 1/3 divided by 3. Y sub 0 is 3 to the 0 plus 4 times 3 to the 1/3 plus 2 times 3 to the 2/3 plus 4 times 3 to the 1 plus 2 times 3 to the 4/3 plus 4 times 3 to the 5/3 plus 1, 1, 4, 2, 4, 2, 4, 1 times 3 to the 2nd power. We should get some kind of an approximation for that and see how close that will be. So I have 1/9 times 1 plus 4 times 3 to the 1/3 plus 2 times 3 to the 2/3 plus 4 times 3 to the 1st plus 2 times 3 to the 4/3 plus 4 times 3 to the 5/3 plus 1 times 3 to the 2nd. And I have an answer. I get 7.2826. Remember, I'm doing the integral from 0 to 2 of 3 to the x dx. We're trying to approximate that. So I'll go ahead and use my graphing calculator to get an approximate solution. The integral from 0 to 2 of 3 to the x dx. What does my calculator give me for that? I think I've done this earlier in the lecture, but that's okay. We can do it again. Integral from 0 to 2 of 3 to the x dx. And I get 7.2819. So I feel pretty good about my answer here too, that using Simpson's rule, we get a pretty good answer. And the reality is Simpson's rule is a whole lot more efficient than the trapezoidal rule. So if you've got a choice of which ones to use, Simpson is better, it converges faster. What I like about the trapezoidal rule, though, is it's very easy to see how the geometry works, right? You can go ahead and construct the 4 trapezoids and make it work. Cannot use Simpson's rule if n is odd. To use Simpson, n must be even. Now, to use trapezoidal rule, n could be even or odd, right? But you're right, 1, 4, 2, 4, 2, 4, 2, 4, 1 will not work if n is odd. N has got to be even for that to work. So what do we do today? We did numerical integrals. First, we used a Taylor series to approximate an integral that we could not have done otherwise. And then we introduced a geometric version of the trapezoidal rule, 1, 2, 2, 2, 2, 2, 1, multiplied by a half, as well as b minus a over n. And then we introduced Simpson's rule. I think you remember on Simpson, change in x divided by 3, and then 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. Why do we do this? Because many integrals cannot be done. There are not antiderivatives for most functions. So if you need to go ahead and approximate a definite integral, the Taylor series is a good tool. Trapezoidal rule is a decent tool. Simpson's rule is a better tool. So that'll conclude this lecture. And check your email to see what is to come. And hopefully I will see some of you tomorrow in the Math Learning Center, SEO 430, around 3 o'clock to work on some problems. Have a great night, and thanks for showing up live.